Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. We started a topic last time. I think we did one example. Optimization. There we go. So let's just jump back into this. Yes, I believe I did example one. Not there, not there, not there, not there. Here. Okay. So we looked at optimization. Very, very important application of derivatives. There are other ways to do optimization, but whenever you're doing it with calculus, this is sort of the idea. We went over this last time. So for us, in the real world, it's a very important application. For us, it's going to be like a word problem on a test, right? We want to know how to do these problems. There are going to be several types of word problems. So you're going to have, your exponential growth and decay problems. You're going to have your related rates problems. You're going to have your optimization problems. Is there another one? I think that's about it for like the word problems where there's like a huge paragraph asking you to do some stuff. Okay. So optimization is the process of making something as good as it can be within some restriction. Okay. And in order to do that, these were the 6 steps that we went over. 6 steps like related rates, but the steps are very different from related rates problem, except the first 2, which is to read the problem carefully, recognize what kind of problem it is, and draw a diagram if possible or necessary, and label it appropriately. After that, things change. For optimization, you're going to need to set up 2 equations, not just 1 equation. So you're going to set up your constraint equation and your objective equation. The constraint equation, remember, is the equation that describes the thing that is restricting you, the thing that is a constraint is what we call it. So you have an equation that describes your constraint. And remember, the constraint is also usually going to be the thing that's given to you. So it's going to be the thing that they're going to tell you exactly how much of that thing you have, right? So they're going to be like, oh, you only have 100 feet of fencing, or you only have 50 square feet of area to do this with, or you only have 16 pounds of blah, right? They're going to tell you something, and that's going to be your restriction. You can't use as much as you want. You only have that amount, right? So you come up with an equation to describe that thing, and that's your constraint equation. Then there's going to be the thing that you want to make as good as it can possibly be. And in our context, as good as it can be basically means to maximize or minimize something. So you'd want to maximize profit, you'd want to minimize cost, that sort of thing. And you come up with an equation that describes that thing. Once you can do that, now you have your 2 equations set up, you can move on to the next step. What will happen with your objective equation usually is that it will have several variables in it, which is not good for us in Calc 1. So what you want to do is you want to change your objective function into a function of 1 variable. That way we can use the calculus that we've been learning this whole time in that equation. So you'd get the new objective by solving for 1 variable in your constraints, plug them into your objective, and then you now have the objective in 1 variable. At this point, you can start to maximize or minimize it, right? And in this case, the absolute max or min is what we'd want, except you'd realize that a lot of the time the endpoints don't need to be checked really. You should look at them, but a lot of times the endpoints are going to be so extreme that it's not going to solve the problem. But it could be. There are a few cases in which I don't really envision me giving you that kind of problem, but it could happen. It'll happen in the homework, I think. And so, yeah, find the absolute max and min. But usually it's going to be a relative max or min that's going to do it. Then you're going to answer the problem, pretty much. So something very specific is going to be asked in the original problem. Make sure that you end the problem by giving them that thing, because there are going to be several ways you can go after part 5 and to just give some random piece of information. No, there's going to be a very specific piece of information that you're going to want to give, and that leads you to that. So these are just some examples of word problems that you can see in this topic. We are going to get through the first 5. That was the plan. So I did the first one where I illustrated all those steps. Read your diagram, your constraint equation and your objective equations, getting the new objective by solving for one variable in your constraint and plugging it in. You'd maximize it. Here you'll notice that this guy was an upside down parabola. You could have found the maximum by a vertex, but I decided to show you the calculus way because you won't always be that lucky to get a parabola or a quadratic. So now you maximize it. You'd realize that the endpoints won't solve anything because your endpoints would literally mean you have no enclosure. And so we got a relative max point, and turns out that solves it. So we went in and we plugged that in. And because in the original question, we were asked for the dimensions, right? Another way to ask for dimensions is to ask for a design. So we made sure we had the X, which was our length, and we went to find our Y, which is the width. And so we give them the dimensions, right? They could have asked for something else here, like what is the maximum area, in which case you wouldn't even need to find the Y. You would just plug that back into this function. Once you find the X, just plug in 25 into this function, and that will actually give you the maximum area. And then that would be your answer. So it's going to be asking for something very specific. So we're going to try these for next time. And that is what we're going to do now. So optimization. Already read through that. Here are the things that I wanted you to try for next time. And we're going to jump into that right now. Okay. Move these off to the side. Okay, so here is the first problem. Design an open rectangular box. Right? So it's a box that's open, meaning no top, but it has a left and right side, a back and a front, and a bottom. Having a volume of 36 cubic inches, that minimizes the amount of material required for construction, right? Because we want to save the earth. Okay, great. So let's do it. So one, we're going to read, okay, which we just did, done. So I know it's, first of all, an optimization problem is what I'm looking at, because we know the difference. So for exponential growth and decay, it'll be stated outright, it's exponential growth or decay, or it'll say something like, oh, it grows proportional to its current size, or you'll see something like a radioactive element, or something like that. That's kind of a giveaway for exponential growth and decay. For related rates, the giveaway for that is that you're going to be described several quantities. You're going to be given the rates for some. You're going to ask to find the rates for the other one. For optimization, the thing is they're going to tell you some kind of restriction, and then they're going to ask you to minimize or maximize something or make something as good as possible, right? So that's how. So read, we know it's an optimization problem. Let's actually move on. So got our diagram. So we want an open rectangular box. That's kind of, right? Okay, so I have an open rectangular box. Now, what do they tell us about the box? It has square ends, so the left and right side are squares, which means to properly label this, I would want the same length on both sides there to get a square. Now, on the other side, I don't really know what that is, so I will label that something else, like a y. Right? So you wouldn't want to label this with 3 different variables. Yeah, label the diagram. But remember, you have to be very careful with your labeling because a lot of things can go wrong with your labeling, both here and in related rates. Sometimes you label something a variable when it's constant and students end up messing up because of that. And sometimes you're using too many variables and you can mess up because of that as well. We're told that this has square ends, so we want the length and the width to be the same thing for the left and the right side. Right. Okay, so that's our diagram. Moving on to step 3, we're going to find our constraint equations and objective equations. So remember, the constraint describes the restriction. What is our restriction? Volume must be 36 cubic inches. Volume can't be whatever you want, has to be 36. So here, volume is 36. What that means is length times width times height is 36. So that is our constraint equation. Objective, what do we want to do? Minimize the amount of material used. Okay, so we want min surface area. Let's call this A. So we know that A is the surface area. So we have to do like left. So the surface area, we're going to do it by taking the area of each side. So we're going to worry about the left, the right, front, back, bottom. Okay. So area on the left, the left is a square, so it's just x squared. Area on the right is also x squared. On the front is this side here. So that's going to be xy. The back is this guy here. So that's also going to be xy. And of course, the bottom is this part here. So that is also going to be xy. So what we have is our A, the area, is 2x squared plus 3xy. And that is our objective equation. Moving on to the next step, 4, we're going to need a new objective. So we're going to solve for one variable in the constraint, plug it into the objective. Here, I would solve for y, right? Should mention, could solve for either. But y is nicer. Because if I were to solve for the x, I'd have like a radical, right? I'd get a square root of, I'd get y in the denominator, then have a square root of y in the denominator. It's kind of weird. Okay, so, but solving for y is nicer. To avoid the radicals. So now I can take that y and I can plug it into the area. So this means that A is going to be equal to 2x squared plus 3x times y. And so that is our new objective. Okay. So we read the problem, drew our diagram, had square n, so we labeled it like that. Constraint was volume. Objective was to minimize the amount of material used. We can do that by minimizing the area, the surface area. Surface area had two variables in it, x and y. Wanted one variable, so I solved for one in the constraint, plugged it into the objective. This leads us to the fifth thing. We're going to want to maximize or minimize. In this case, we want to minimize. The last time we wanted to maximize, as you might recall. But here we want to minimize. Now, that doesn't really change anything that we do. You just need to know that the minimum is what you're looking for. So if there are several solutions, you want to know you want to pick the minimum one. So the one that gives you the minimum point. So here, of course, we're going to solve for a prime. This is going to be 4x minus 3 over 36. 3 times 36 over x squared, because the derivative of 1 over x is minus 1 over x squared. And so for critical points, you need 4 over x minus 3 over 36 over x squared equals 0 or undefined. Now, it's undefined when x equals 0, but this here makes no sense. We would not have a box, right? So I'm going to pretty much ignore that part. So we move on to this part. So we have 4x is equal to 3 times 36 over x squared. Can multiply both sides by x squared. And so we have x cubed is equal to 3 times 36 over 4. So now we're going to want to find x. That's going to be the cube root. Now, 4 goes into 36. In fact, it goes into it 9 times. Was someone saying something? Heard like a microphone go. Okay, so then this would be x equals the cube root. Well, that would leave you with 27, which means that x is equal to 3. Now that's the only answer, so we know that's going to be the answer. Not necessary to check, but you could technically, right? So you have 0 and you have 3, and you'll see that this is a minimum. Okay, moving on. And of course, at 0, it doesn't work. Derivative is undefined. If you're at 0, it's not going to work. Going off to over here, some far point down here, which would have you use up the max area in one dimension. That also won't work. You also notice that you are increasing, so you only get bigger by going to the right. It's not what we want. X equals 3 is going to be what we want. So that leads us to step 6. Answer the question. Question said to design a rectangular box, which means we want to tell them the length, the width, and the height. So so here we have our x equals 3. This means we need the other dimension. The y is 36 over x squared. It's going to be 36 over 9, which is 4. And so the best box is a 3 by 3 by 4 box. Right, where this guy is like the width, the height, length. Right, so it's obvious the 3 and the 3 gives you the square side, so that's going to be the dimensions of the left and right side. Should be 3 inches by 3 inches, and the other dimension should be 4 inches. And that's the best box here. That would give the minimum amount of materials. And that's our optimization problem. Again, go through the 6 steps, read, draw your diagram, you label it appropriately based on the problem. Using the diagram to help you, because here I'm visualizing what I needed to add into the equation by say, oh, there's this side, there's this side, there's this side. I know I counted 5 sides in this diagram, so I know I needed to add 5 areas together, for example, and I can look at the labeling to see how to add them. So just like with related rates, you draw the diagram to kind of help you set up the equations. So you set up your constraint and objective equations. Your objective is going to have more than one variable in it. So you're going to solve for one variable in your constraint, plug it into the objective. You're going to maximize it or minimize it. Whether either one, you're going to do the same process, find the derivative, find the critical points, test the critical points if necessary. Ultimately, you're going to come up with an answer at that point. What one of the variables need to be to give you the max or the min. And then you answer the question because it's going to ask for something very specific. So make sure you give them that thing, right? So you can't just say x equals 3 is the answer because you would be wrong. That wasn't what you were asked. What is x, right? You don't even know. So you want to say, okay, length with height, that's what I want. The x is just the height and the width, and I can find the length by finding y. Okay. So hopefully there are no questions with that. I mean, if there are, it's okay. You can ask me, but I'll do that one slowly. Are we okay with this? Do we have any questions here? Anything that's not clear? No. Okay, let's keep going. Here's another one. A rectangular corral, 162 square meters to be fenced, and then divided by a fence into 2 sections. So it's shown in the figure to the right. So we're going to build a fencing in a rectangular, and then we're going to build a fence going straight up the middle. So find the dimensions of the corral. So the amount of fencing used is minimized because, you know, we want to save the whales, save the earth, all that good stuff. All right. So what do we do? So we were kind of given the diagram to visualize. So 1, can read. 2, diagram. Now the diagram was given, but it wasn't labeled. So we'd want to label it. So here's our diagram. And here's how I'm going to label it. I'm going to label it this whole edge here. It's going to be X. This edge here is going to be Y. which of course means that this inner edge here is also y. Should mention here, get some options here. You could label this, could label as, it might be a knee-jerk reaction to actually label it to the divider, call that x, and then you label this other part also x, and then this part y. But I think that just makes your calculations harder for sort of no reasons, because now you have the entire length being 2x. So this is just 2x, right? It's just, to me, it's needlessly complicated. But that's being said, it's not wrong as long as you describe properly what you mean, as long as you say in the final answer, oh, x is just the distance from one end to the divider. Once you actually make that distinction, it'll be fine. But your answer, your x would be like half the length of my x. But they should give the same answer. Like you should know that for your x to be equivalent to my x, you need to double it up. But just having that 2 there, it seems needlessly complicated to me. It's not wrong though, but just would mention that it would be okay if that's how you thought of labeling it. That's fine. You should get to the same answer that I do. Just make sure that you account for the fact that your x is different from my x. But you will ultimately get to the same answer. Just like having that 2 there is just like, why? Why do I need that 2 there? So now 3, I'm going to find the constraint and objective. So remember, constraint is what we have a restriction. If you read this, it says that 162 square meters. So that is area. So here, this means that x times y equals 162. Had you labeled it like the diagram on the right, you would have 2xy equals 162, then you divide by 2 and then use that equation. But here I can just go x times y equals 162. That's my constraint equation. Objective equation. We want to minimize the amount of fencing. So that's a perimeter. We had the opposite problem in the farmer's situation, right? The perimeter was our constraint and we wanted to maximize area. Here the area is our constraint and we want to minimize perimeter. So the perimeter for me would be x plus x, right? Because there's going to be another x right here. That's a length x. And then I'm going to have 3 y's. So notice that I would have 2 x's and 3 y's. So here I can say A, not A, let's use P for perimeter. P is 2x plus 3y. That's going to be my objective equation. Okay. That brings us to step 4. Find a new objective. Because that one, while it's correct, is not usable. So what we're going to do is we're going to solve for the x or y. It really doesn't matter who you solve for. So let's solve for y. Two x plus 3y. Which, I mean, looking at that, it was probably a little bit nicer to solve for the x instead, because you have the 2 times 162 instead of 3 times 162. I don't really think it's a big deal though. But you're allowed to, in general, I just want to kind of, I'm writing these statements because I just want you to know it's okay to solve for either one. Anything that makes your life easier is okay. Like whichever variable you find first is not going to matter too much. But here is our new objective. So now we move on to step 5. We're going to want to maximize or minimize this guy. And in this case, we want to save the whales. We are going to minimize. And that's what we were asked. Amount of fencing is minimized. Either way, we're going to need the derivative. P prime is going to be 2 minus 3 times 162 over x squared. Critical points. This is going to be P prime equal 0 or undefined. It's going to be undefined where x equals 0. Of course, you're going to reject this. Doesn't make any sense. We wouldn't have a corral if the x was 0. So for this part, we have 2 minus 3 over 162 over x squared equals 0. This basically means that 2 is equal to 3 times 162 over x squared. Or in other words, your x squared is equal to 3 times 162 over 2. Now 2 goes into 162. 2 goes to 16, 8 times 81. Yeah, so that goes into 81. So this is x squared equals 3 times 81. Now 81 is 9 squared. So if I take the square root of 81, I would get 9. So here I would just have 9 rad 3. Now, of course, we are going to reject the negative. Not in a quantum realm or anything. So 9 rad 3 is going to be our x. So now we move on to 6, answer the question. Find the dimensions of the corral so that the amount of fencing is minimized. So I want the dimensions. So I know my x is this. So I know my x is 9 rad 3. This means that my y is 162. It was 162 over x. Yes. So this is 162 over 9 rad 3. Does 9 go into that? 9 goes into this 1 time, remainder will be 7. 9 goes into 72 like 8 times. Is that correct? So dimensions would be 9 rad 3 by 18 over rad 3 feet, meters. Where the 18 over rad 3 side is divided by the divider. And that's what we'd have. And I assume there are no questions on that part. If there are, you can let me know. Fix this in here. To fix the file a little bit. All right. Let's do another one. So, I mean, there's nothing new to teach here. It's just me trying to get you used to the process. Because really for problems like these, that's what it's going to come down to, is how used to the process are you? Okay. So here's another example. A cylindrical can without a top is to be made with 8,000 pi cubic meters of liquid, right? So cubic meters is volume. So that tells you here, volume is constraint. Find the dimensions of the can, which will minimize the amount of material needed to make the can. Again, that's surface area. Oh, I said right there, that is minimize the surface area. Normally in like a test or a quiz, I wouldn't have said that. I copied this problem from somewhere. They were very nice to tell you what they wanted to minimize. I would have ended at that sentence right there, actually. So yeah. I mean, for full transparency, I should say that Jhevon probably wouldn't tell you this. Okay. All right. Let's actually get through it. So cylindrical can without a top. All right. So we read this. This is boom. We read. No, it's an optimization, all that good stuff. 2 diagram. We've seen cylindrical cans before. They look like this. And here it's It's open. All right. So now we want to know the dimensions of the can, which means there is like a height, call it H. There is also a radius, call it R. We want to know the radius and the height of the can that would minimize the surface area in a can that actually holds this much volume. Right? So we know we want the can to hold that much volume, but we want to not waste materials on creating such a can. And so now we move on to 3. We want to talk about the constraint equation and the objective equation. Constraint is what you want to maximize or minimize. No, objective is what you want to maximize or minimize. The constraint is the restriction, remember. So we already saw that our restriction was the volume. We already know how to find the volume of this. We spoke about this in the last section. This was, we want V equals 8,000 pi, but the volume of a prism is the area of the base times the height. So this is going to be pi r squared h is equal to 8,000 pi, or in other words, r squared h is equal to 8,000. Objective, we want to minimize surface area. Now, I don't know if you'd recognize this, but I'm going to tell you the trick for finding the area of a can. So the idea is, if you have a can, what you can do is you can cut and unfold. So you'd realize that the can is made up of a couple parts here. So you're going to start unfolding it. Right, and you're going to have that base, which is a circle. And so eventually you can unfold it and it'll be a rectangle. And you would have one circle. If it was a closed can, you'd have 2 circles. So you'd have here where this is your R. You would also have here where this is your height. And then here, you'll recognize that as, well, that was the distance around, right? So we unfurled it. That's the distance around the can. That's just circumference. So that is 2 pi r. So the area is going to be the area of the side of the can plus the area of the circles if there's a top and a bottom. Here we only had a bottom. So this means that our area is pi r squared for the base. And then we add, it's a rectangle now, so it's length times width, 2 pi r h, and that is going to be the side. So that is our objective, right? And you don't have to sketch this. I just want to explain to you where this equation comes from. You want to find the area of a can. What you do is you slice it, you unfurl it. You'll realize that the side is really just a rectangle, where the circular part is just going around the disc at the base. So it's going to be the length of the circumference, and the height is going to be the other dimension. So that will help you find the area. If it was a closed can, of course, you would have 2 pi r squared because there would be a disc at the top and the bottom. Okay, so hopefully that's clear. So now we're going to find the new objective. So we know that r squared h equals 8,000. This means that I can solve for h. This is 8,000 over r squared. This means that our area is going to be, I'm going to plug in that h. So it's going to be pi r squared plus 2 pi r h. So this means our area is pi r squared plus 2 times 8,000 pi over r. Move on to step 5. We're going to maximize or minimize. Here again, we want to minimize. We're going to find a prime, which is here 2 pi r minus 2 times 8,000 pi over r squared, set equal to 0 or undefined. Normally I would put that in blue. Let's put that in blue. Set this 0 or undefined. Undefined would mean r equals 0. Makes no sense. Well, it does, but it would be no can. And so this means we need 2 pi r minus 2. Let's move to the other side. 2 times 8,000 pi over r squared, which means I can multiply by r squared to get an r cubed on that side. And then I would divide by the 2 pi. So of course that cancels. And so this means r cubed, or r, is going to be the cube root of 8,000, which is 8 times 1,000. Cube root of 8 is 2. Cube root of 1,000 is 10. So this means our r equals 20. Not the final answer. We were asked for find the dimensions. So we also need the height. So now move down to step 6, answer the question. So r equals 20. This is your radius. H equals 8,000 over r squared, if I recall. Yes. So this is going to be 8,000 over 400. That's just 80 over 4. That's also 20. So that's going to be your height. Forgot to spell height, need sleep. Okay, so this means those are the dimensions. Is radius, what was the things here? Meters, equals 20 meters, height equals 20 meters. That's the best can. Okay, last problem. Manager of a department store wants to build 600 square foot enclosure. So that's an area, right? Because it's square foot. So this constraint is area. So he wants to build a 600 square foot rectangular enclosure in the store's parking lot to display some equipment that obviously they want to sell. 3 sides of the enclosure will be built from redwood fencing at a cost of $14 per running foot. The 4th side is going to be cement blocks at a cost of $28 per running foot. Find the dimensions of the enclosure that will minimize the cost. So we want dimensions that will minimize cost. Cost is objective, want to minimize. Or a little bit more, to get a little bit more specific, could think of this, find the dimensions. That part refers to the answer the question part. And minimize cost, that is the objective. Okay. So that's how you're going to read this. You're going to, of course, recognize it's not any of the other kinds of word problems, but once you kind of figure out that it's an optimization, you automatically now want to kind of start setting up in your head what's going to be the objective, what's going to be the constraint, what do I actually want to find, and you need those in your head. Okay, so in this case, area is going to be the constraint, cost is going to be the objective, and I want to find the right dimensions. Now this problem is a little bit more challenging to set up, I think, than the other ones, because different sides are charged. You have a different cost for each side. Not totally harder or anything like that, but it's different. And I guess this could be a problem that would show up like on a final or something like that. So this is like a final level problem here, a final boss. The other ones I can put on a test or a quiz. On a final, it might be something like this. Or even some of the others would be good enough for a final, to be honest. It's more important that you just know how to deal with this problem type than for me to give you some super crazy problem to set up some random function. So that's not going to be the goal. The goal is to, do you know how to set something up and use derivatives to get the best possible solution? Okay, so we go to 1, read. Let's make sure that's roughly the same size. 2, diagram. So here's where you really want to make sure that you're capturing the essence of the problem. So, so there is a rectangular enclosure, but one of these sides is not like the others. So let's this part here be the cement blocks. And then the other part is the redwood. So this side is redwood, that side is redwood, that side is redwood. And I know I want this to be 600 square feet in area. Okay. So now we're going to label this. So let me label the side that has the cement blocks along it, X, and these guys here, Y. Now that automatically starts to give me some perspective on how we're going to set up these equations. Now let's talk about the constraint. Constraint is the area. So this means that X times Y equals 600. Objective, we have to be a little bit more objective here. Okay, no, that pun totally did not work. So we know that this length is X, so we need the cost. We were told the cost is $28 per running foot. So if I put in cost here, so this is going to be 28X, right? And then the other side is going to be 14X. And then this part is going to be 14Y. This part is going to be 14Y, right? So these are the cost. So per running foot, that is going to be the cost of building this fence, which means that my cost equation is just going to be the sum of these. So I'm going to have, looks like 42X. Plus 28Y. That's going to be my objective. Moving down to step 4, get the new objective, because that's too many variables there. I know that X times Y equals 600. Now, I would rather multiply by 28 than 42 maybe, but actually 42 is the answer to life, the universe, and everything. So I might solve for the X, but no. Let's go to but you know what? I always solve for the Y. I don't want you guys to feel like that's like what you should do. I'm going to solve for the X just for fun here, because I don't want you to think that you always have to solve for the Y. Solve for X. So now this means our cost is, I'm going to replace the X with that. So I'm going to have 42 times 600 over Y plus 28Y. Now moving on to step 5, we're going to maximize or minimize. Here, once again, we want to minimize. Doesn't matter, either way, we're going to find C prime, which in this case is going to be minus 42 times 600 over Y squared plus 28. Set that equal to 0 or undefined. It's undefined if Y equals 0, reject. So now we end up with 42 times 600 over Y squared equals 28. Then I move the 42 times 600 over Y squared to the right side, and then I flip the equation. It doesn't really matter. So now we would have Y squared is going to be 42 times 600 over 28. So Y is going to be the square root of all that. Now, I did do, did I do this last time? Technically, this is a plus or minus, but of course you reject the minus. Cube roots would root the same sign. Yeah, I did do the plus or minus. Like just because it doesn't mean we could. It's not anarchy, right? It's not a free for all. Like there's still, when you take the square root of, you get a plus or minus. Like what do you want me to do? Okay, so I see that I got a plus or minus, but I reject the minus. I reject sir, and then yeah, we are going to do 42 times 600 over 28. Now, 14 goes into that 2 times. And 14 goes into this 3 times. And then 2 goes into that 300 times. Which means this is the square root of 900. So that means y is equal to 30. Okay, what were we supposed to do? Find the dimensions. Okay, all right. So we know that y equals 30. This means that your x is going to be 600 over y. That's 3 into 60. That is 20. So this means dimensions. It's going to be a 20 by 30 foot enclosure where the side with cement blocks is 20 meters. So I gave you the dimensions and I told you where you want to put the blocks. And there we go. That is that. That is optimization. Did a lot of examples there because I just want you to get used to the process. Now, the next thing we're going to do is attacking the area problem. We're actually going to make, going to switch things up significantly. So this is what we're going to be doing next time. Yeah, so a part of the reason why I've been moving so slow is lack of sleep. But another part is that, well, I didn't want to finish too early and then force me to kind of start this topic. I think it'll be just nice to start it on its own. So I'll leave this in the notes for you. I'm going to explain where all this stuff is coming from, and then we're going to do some problems together, which I left space to do an example here. So we will do that next time. But yeah, we're pretty much done with derivatives and their applications. We're going to be doing the other part of calculus, which I mentioned to you, which is integrals. So integral calculus. And we're going to spend a little bit of time on that. And I know it's almost at the end of the semester, but that's totally normal for a Calc 1 class. Normally, Calc 2 is the class where you go into the second part of calculus, integration and integrals and antiderivatives and that sort of thing. But Calc 1 usually just starts to introduce you to that. So yeah, next time I will be introducing you to all that stuff. And I'll leave the notes here. But I don't think you necessarily have to read through it. In principle, I think it would be very clear as I'm explaining it, what's happening, even though it might look complicated in the beginning. So yeah, that is that. So that is optimization. And yeah, eventually you'll get homework on this. Well, now you'd have homework on all of chapter 4, which should be up today. But nothing else to say really. Yeah, let's end there. It's a nice place to end. So we finished the majority of the course, like 4/5 of the course, which is awesome. Yeah, time to wrap up. Hopefully you guys are okay going into finals week. The final exam schedule is up. I believe I sent you guys the link a few weeks ago. So make sure that you don't have clashes with your finals or anything of that sort. I think someone asked me about the timing of the final and when grades were due or something like that. I don't think the issue you raised, I don't think is going to be an issue. So that's, I guess I'll just say that. So yeah, usually the grades are due 3 days to a week after the final is given. And for what was mentioned, it's okay. So whenever the grades are going to be due, it'll be fine. But we'll end it there. Thank you for your time and attention. I will see you guys in the next one. Okay.